All right, line Q1, learning task 1, which is going to talk about identification of conductors. In other words, what is a conductor and what makes a conductor? Well, the very first part of that whole learning task starts talking about different types of conducting materials. And there's a chart that's going to be shown inside there as well. But each material is going to go and have a bunch of things that are going to be held in tension. When we select what they are going to be. Things like cost, are going to go and be weighed into there. Things like weight. If you are pulling cable or if you're having to lay cable inside of a trench, let me tell you, you want to see aluminum conductors, not copper conductors, right? Because that aluminum is only going to be a third of the weight of the copper that we are going to go and have. That being said, aluminum is great, but it also has got some really poor oxidization that we are going to go and have. Oxidization is another term for rust. We refer to it as rust. Rust is just steel oxidizing, iron oxidizing, I should say, not steel. But oxidization is just going to be a buildup of layer, and some of these things can be really damaging. Aluminum oxidizes very fast. There's going to be two other ones that we don't really look at as much, but it's going to be the flexibleness of them, and it's going to determine whether or not my actual manufacturers can go and do these. Ductility and malleability. When we make a wire, what happens is that the wire is going to start out as a billet of material, and we're just going to go and successively draw it through a number of dies to make it smaller and smaller. Conversely, if it's really malleable, we might go and hammer it down into sheets and cut strips out of that are going to be used for like bus bars or for like some of my metal wound resistors, things like that. Ultimate strength plays in. Ultimate strength is going to be how much tension I can put on either end of a piece of wire before it's going to go and break. Copper's got pretty good ultimate strength. Steel has got incredible ultimate strength. Aluminum has pretty crappy ultimate strength. If you've ever worked overhead lines, you know that there's going to be a messenger cable or a steel cable in the center. That is going to be used to support the weight because otherwise the aluminum would just pull apart. Oxide resistance is going to be different than oxidization. Oxidization is just how quickly it rusts. Then taking a look at the actual oxide, is that oxide going to be electrically conductive or not? Aluminum has got a very high oxide resistance. In other words, it is not very conductive. Whereas silver has got very low. If we get tarnish on silver where it starts forming that kind of blackish layer, that's fine. It still doesn't make much of a difference to it. And for gold, we don't have, anything. That's why gold has always been such a historically valuable metal, gold and platinum and stuff, because they do not oxidize. They don't tarnish or, dull out or anything like that. And as a result, we don't get any sort of an oxide resistance on them. Contact resistance, that's going to be this one down here, is the resistance per area of contact between two conductors at fixed values of pressure. These are engineered values over here, but it's going to depend upon the type of material it's going to have. If we take a look at copper over here has only got a contact resistance of 100. When we press copper up against copper, it relatively easily flows. Aluminum, not as much so, which means that we have to be careful with the aluminum conductors that we are going to go and use inside of here. Conductance is going to be opposite of resistance. It's measured in a value that is going to be called Siemens, same as the manufacturer, Siemens over here. And it's just going to be the inverse of resistance. Something can either have a high resistance or a low conductance, or we can say it can have a high conductance and a low resistance that we are going to have. We don't use it very often, but copper has always been what we measure everything else against. Insulation required per volume. This is going to go and be just for the amount based upon a weight. It's not as much of a big thing that we look at inside of here, but it's going to deal with the amount of insulation. We see that aluminum requires a bit more insulation than what copper would go and be. Let's take a look at the first two columns because they are going to go and deal with our two most common types of conductors. We'll just erase all of that. We don't need that inside there. And let's take a look at copper and aluminum. Copper is excellent. It works very well. It's got a very high value of conductance. It's got a very low value of resistance. This is the R that we use inside of that formula. The K that we use. R is equal to K times L over top of CMA. So that material type is going to be a low value, which means if I've only got 10.4, I'm going to go and have a lower value of resistance than aluminum, which has got 17. I do see that copper is actually a better conductor than gold. We have this, erroneous belief that gold is a better conductor. Gold is not a better conductor. It just performs better. It doesn't oxidize and it's more ductile, etc. And I take a look at silver. Silver is actually going to be my lowest amount of resistance for a material type itself. But copper, it's got very good conductance, fairly low value of resistance. Its oxidization is slow. It can tarnish. You've all seen green copper before at some point or another. And when it does tarnish, it can have a high oxide resistance. We do need to make sure that our joints are going to go and be tight. Make sure there's good copper-to-copper conduction. And as long as we've got that copper-to-copper, joint over there, there shouldn't be room for oxygen to get in between. This is why we want to do up our joints tight, and why we should be twisting our wires with a set of pliers before we go and put our wire caps or morettes onto those things. Copper is heavy though, and it is going to go and be expensive at this point. Copper prices have gone up. You hear bosses talking about that all the time. Copper prices are going up again. Copper prices are going up again. Make sure you get your order in so you know you don't have to pay extra, etc. It is not going to be nearly as expensive as some of my other ones. Obviously gold and silver are going to be quite expensive. We'll talk about their use in a second, but it is getting more expensive. As a result, when it comes to larger gauges of wire, we prefer to go and work with the aluminum. The aluminum does have a lower cost, and it has got a third of the weight, which means that it is a lot easier on large conductors to put it in. It is also going to be easier for us to go and bend in a lot of cases. That is different than ductility and malleability. Ductility and malleability is how we can work it into a conductor shape or into a plate shape. The actual ability of us to bend them in the field, aluminum does bend easier than what your copper is going to be. So we prefer it for our large ones. However, it does have fast oxidization, almost instantaneously, that it's going to start forming an oxide layer once we expose it to oxygen or strip off the insulation, which means we have to go and use some sort of a penetrox on there. If you go into your code book, the code requires that we do have an antioxidant chemical. An antioxidant chemical is going to be what we refer to as penetrox or Nolax, are the two most common ones there. What they need to be able to do is they need to be able to penetrate the oxidization and prevent it from reforming. You cannot just go and put, anything onto those splices. They do need to have something on it. If you don't place anything onto those splices, they will oxidize, and that oxidization is going to be a high value of resistance, which is like having a series resistor in line with that. Usually what you should be doing is brushing them, not with a really stiff brush, but with a light brush. You're going to go and brush off any oxidization because it is soft, and then you are going to go and apply the penetrox onto them. Make sure they're fully coated. When we take a look at electrolysis, we also have that issue with aluminum where it tends to go and send electrons from itself to other metals that are close by, steels or things like that. When we have got improper types of morettes that you're going to use. If you've ever done aluminum houses that you've had to pigtail out, there's going to be those purple morettes that have got a little bit of penetrox inside there to prevent the oxidization, and they're going to be rated for use on aluminum. See, with some receptacles and switches and things like that, they're not going to be rated for use on aluminum. It will say Cu, that's going to be my short form for copper, or Al, that's going to be my short form for aluminum, if it is rated for that. If it is not rated for that, the reason for it is because the metal that is being used on the contact surfaces will cause electrolysis, where they're going to go and eat away at each other. We're going to see that inside of cathodic protection, where we're going to talk a little bit more about electrolysis. That's why we have to use the correct morettes, not just because they got the penetrox inside them, but because they've got the correct metal. Same with the correct devices. Last one that we have heard about before as well is cold flow. Cold flow is just the fact that aluminum reacts to being under pressure by equalizing. Remember how nature tends to want to go in balance? Aluminum tends to self-balance quite easily. If we place it underneath pressure, underneath a lug, it will go and flow out from underneath there to go and reduce that pressure. This is why when you're dealing with aluminum, what you need to have is you need to have a lug that is sized correctly. The sizing on the lugs, just because we can fit a wire underneath there, does not mean that we should necessarily, fit the wire underneath. What I'm talking about is if I've got a lug that is rated for 2/0 over here, and I decide that I'm going to go and place we'll say a number 8 aluminum underneath there. What happens when I place that number 8 aluminum underneath there is that this hole over here is rated based upon that size that we are going to go and have. And we know that if you've worked with these lugs before, they're going to go and have a threaded insert that is going to go and drive down, and usually that threaded insert is going to be flat. So if I take a look at a number 8 conductor placed inside of there, that number 8 conductor will be able to cold flow out to either side to start filling that gap, and it will go and lose that. We compare that to something that, whatever the minimum size was supposed to be. Let's try and redraw. Too big over there. We compare that to whatever the minimum size is supposed to be. This thing was sized from 2-aught up to 4-aught. My 2-aught, when I'm going to press it down inside of there, is going to mostly fill it. It's only got a small amount that it can go and cold flow out. Therefore, it's not going to be able to reduce the pressure all that much off of it. There are problems with aluminum. It's not a perfect type of conductor, but overall, it is worth it because it is cheap, it's light, and we can manage it. We can bend it, we can drag it around sites and things like that. Just because something is made with aluminum doesn't mean it's an inherent fire risk. I know some people don't want to go and buy houses that have got aluminum wiring in there. I want you to just think for a second, if that house has been wired in aluminum since the 70s, and if it hasn't burnt down yet, what makes you think that it's going to burn down the instant that you go and buy it because it's got aluminum wiring, right? It says as soon as you start disturbing that aluminum wire that you start to go and have problems with it. But overall, aluminum wire in and of itself is not dangerous if it is treated correctly. Silver and gold, we'll talk about those ones just really quickly. They're going to be used inside of fine components, electronic components, really where we need to go and make subcompact type of circuits. Actual circuit boards themselves will use them inside there because we can get a high amount of current flow over top of the small conductor, and that conductor is not going to go and tarnish. If you take a look at copper or aluminum, the oxide, the way that eats in, if you've ever seen anything that's rusted, it's pitted, right? We can't have any oxidation. When you've got conductors that are going to be smaller than a human hair, those things cannot have oxidation because it will eat right through that very fine conductor, breaks the link. So we'll use silver, or we will go and use gold for those types. Steel itself is not usually going to be used as a conductor. What we will use it for is a supporting material. We will sometimes see steel being used for grounding, for transformers. And the reason for that is just simply copper thefts. Bicycle bandits roll up, they nip off the copper, and they run off of it. Steel is pretty much worthless at a recycler unless you're dealing in the tons, and you can't carry that around as, a one-man gig. So most of the time, they're going to leave the steel alone, plus it's harder to go and cut. So you will see steel at this point that is going to be used for grounding. Outside of grounding, we will use it as a messenger cable. A messenger cable is just going to be something that is used to support other conductors, copper or aluminum. Things like a triplex, also referred to as an NS or a neutral supported cable inside of your Canadian electrical code, are going to go and have a central steel conductor, and around the outside of that, then it's going to go and have its copper or aluminum conductors that are going to be carrying the current. The steel is just supporting that thing. We will use steel itself to go and deal with, building enclosures, though. Obviously, it's a good hard material that, when properly, powder coated, etc., isn't going to break down. So we do have to bond them together because it is still conductive inside of there. We'll talk about that in grounding and bonding. The other place we see steel used is in the actual grounding electrodes themselves. Grounding rods and grounding plates, which are going to be heavily zinc coated so that they resist galvanization, is what we call that, the zinc coating. They're going to be heavily coated so that they do not go and rust out, but they're still going to be made out of steel. All right, conductor forms. Let's talk about the different forms of conductors. We have got solid conductors versus a bus bars and stranded, and then we got a multitude of different types of strandings that we're going to go and have. Solid conductors are obviously going to be made up of a solid piece of copper or aluminum. The way that these are formed, they just take a chunk of aluminum, they start pushing it through a hole. And then as it comes out, it's going to be, a smaller size of conductor. They're going to push it through successively smaller holes. They call these things dies. And as they push it through, this thing gets down to smaller and smaller sizes. What happens, though, when this is going on is that it tends to get harder. It gets just through the compression. Overall, it becomes what we refer to as work hardened. You'll see this on old installations where you'll sometimes have pieces of copper wire that are just incredibly stiff. And what's all it is that they were hard drawn, is what we refer to. Most of the time, we deal with conductors that are going to be annealed. Annealing is where the hard drawn conductor is then going to be heated up. And as it heats up, it is going to go and soften back up again. And then, it makes it easier for us to go and bend and, drag it in through holes that we've drilled through the studs and everything else. Solid wire is going to be small. It is going to be number 10, number 12, and number 14 for us as electricians. In fact, if we go into our code book, Table 10D doesn't give us any other options for solid size. We have nothing else that's approved for use in Canada. It will be, inside of your book, it says it's going to be smaller than 8 BNS. BNS is another way of saying AWG is the old brown and sharp. We'll talk about that later on as well. But it's smaller than number 8, so in other words, it is 10 to 14. Bus bars are going to be used for high current applications. These are going to be usually long conductors, and the beautiful thing about a bus bar is we can drill holes and we can mount lugs off of those things so we can tap other conductors off. So we'll see them inside of a lot of our distribution equipment. Usually they're going to be made out of copper or aluminum. We do have other materials, but those are the most common. And then if they are going to be made out of copper, they will usually also be flashed, which means they're going to be coated with some type of metal that is not going to go and oxidize. Even aluminum ones will be flashed as well. Usually it's going to be a nickel coating that's going to be placed over top of it. Nickel's relatively cheap, and it's got a pretty good conductance. It's hard to work with as a wire, but when we use it as a coating, it's perfectly fine. Other types of buses that we do see are going to be these hollow tubes. Now, we don't deal with a lot of hollow tubes on our day-to-day. We have talked multiple times this year about the shred losses. And the shred losses are going to be losses that happen inside of any conductor anytime that my frequency increases, right? If the frequency increases, we get more shred losses. The S for that is skin effect. If I have high frequency applications, all my conductors are pushed out to the outside. So if all my electrons are pushed to the outside edge of that conductor, which means that the inside becomes useless. So why would I bother having it inside there? So high frequency applications, we will use hollow tubes. Same with high voltage. High voltage is just going to be a sine wave that's really tall, which means that my electrons, once again, are going to be moving back and forth with a lot of velocity and colliding. So high voltages are also going to go and increase shred. Anytime that I've got high voltage or high frequency, all of my shred losses have gone up incredibly. Particularly this one over here, skin effect. High voltage and high frequency, we will use hollow tubes. Just because there's absolutely no point in having a core in there because the electrons aren't going to travel down it anyways. They're kind of cool. You'll see them inside of high voltage installations. Sometimes they will actually go and run like cooling components through them. They'll use them for other stuff. Other times inside of some of my high voltage installations, we will go and have hollow tubes, and then inside of that, supported, we will have other conductors that we can go and utilize. So we will have insulators that are going to hold these off on the insides, draw them in kind of like a star, although they are usually ceramic discs, but they're going to go and have another conductor that can be on the inside, and then what they'll do is they will go and vacuum out all the air, because a vacuum is a perfect insulator, or they will replace it with other types of gases like sulfur hexafluoride, SF6, or things like that for the insulation. But specialized applications you will see inside of high voltage. All right, talking about stranded conductors, everybody has seen stranded conductors. We have got two main types that are going to be concentric and then bunch stranded over here. Concentric is where we start with one in the center and everything around that is going to be laid out. Now you see that there are openings. There's little gaps in between each one of these over here, which means that overall my size is going to be much larger. What I have got is two main types of concentric stranding. We are going to go and have what we refer to as concentric and compact concentric. Compact concentric is just going to push these together. Now it is going to be smooth on the outside. It is just a poor quality drawing for this one, but just imagine that that's smooth on the outside. If you strip these off, they're really easy to strip off the actual insulation around the outside because there's no gaps. These ones over here, standard concentric, are really hard, particularly some of the older cables that you might run into in some installations, because when they go and place the plastic around, that plastic flows in, and sometimes it flows in and underneath like that. So my insulation will be going around this thing. It's got all these little grabs. And as a result of all these little grabs inside of here, where it's pushing into each of those, the actual insulation will go and hold onto this conductor, makes it hard for us to go and flex it, put it into position, and makes it really hard for us to strip it. You need to be careful with these, that you pull all those little flecks out. You got to usually do it with like a knife tip or something like that. Concentric stranding is going to go and be a way we can adjust the flexibility as well. The more strands that we place inside of something, the more flexible that component is going to be. So I've got what we refer to as standard stranding. Standard stranding is going to be 7 conductors, which is going to be a single, and then it's going to be surrounded by 6 on the outside. That's what we refer to as standard. Then I'm going to go and have flexible, which is going to be 19 strands. So I'm going to use smaller strands, and I'm going to have additional layers. And then I'm going to go and have what's extra flexible, which is going to go and have 37 strands. Extra flexible, we use that in places where usually our installation is moving. You know, it could be something that's shuttling back and forth along a frame, like a gantry crane or something like that, or a piece of equipment that's got a lot of vibration that we don't want to transfer, so we might use extra flexible. Sometimes we'll hear this extra flexible being referred to as DLO. Diesel locomotive is actually what DLO stands for, but it's a type of cable that is extra flexible because it has to be able to deal with the vibration of being inside of a diesel locomotive, but we're allowed to use it inside of other installations as well. Compact and concentric stranded are going to be the most common types of strandings we will find. We do have some of these other ones, bunch stranded. Bunch stranded are going to be used with super fine wires, and it's going to be inside of what we refer to as fixture wire usually. Smaller than number 12 in most cases. I've never yet seen a number 10 that's made out of bunch stranded, but it's going to be super fine conductors that are just, a whole pile of them bunched together and then insulated around that. We do also have rope stranding, where I'm going to go and have individual smaller strands that are then going to be tied together, twisted together as a rope. Usually these will once again be used for extra flexible ones. If I go with bunch stranding, I can get away with tiny conductors, which are going to be flexible, but they tend to break and to have uneven distribution on the inside. Whereas if I go with rope stranding, because I've got these things twisted into the individual, we refer to these as the lays of the rope, and then I go and twist them together as a stronger one, we end up being able to build off of all the cumulative strength. So it makes it much better for places that require a lot of movement back and forth. Other ones that we do see that aren't listed inside of here are going to be flat braid cable. They talk about using it for battery grounding on a vehicle. We don't do that. We're electricians. What we use it for is bonding together of components. Where you will see it is inside of high voltage situations. Everything that is going to be metallic is going to have to be bonded down, including things like doors. And so you can't rely on the hinge because the hinge is full of grease to go and have that. So what you'll see in a lot of high voltage ones is on the hinge side of a door, there's going to go and be this flat braided conductor that's going to be bolted to the door and then bolted to the metal frame of the door itself. It's a poorly drawn frame. Let me see if I can do better than that. Bolted to the frame itself, and then all of this is going to be, connected back to my main grounding component. Once again, specialized applications where we need to be very, very aware of our grounding, high voltage stations, but we will see it used for that. We'll also see it used for, if you've ever seen a pole top switch, that's going to be one of those ones where you get the pole coming out of the ground, and then mounted on the side of that, there's going to be this bracket with a long arm that goes all the way up to the top, and then there's going to be this bar that's going to come out of there, and you can go and use that bar to go and switch back and forth. There's also going to be a ground mat that's going to be underground for them. And all of that needs to be bonded together so that my operator is going to be safe. We will do that usually with flat braids. All right, that is learning task number 1, which talks about the identification. What we're going to do next is we are going to go into our code book for the next one, and we are going to be referring to pretty much everything in the code from this point forwards.